about applying a lot of these ideas at LinkedIn, and then we're going to see 2 more talks on systems to implement a lot of these big data computations focused on graphs. So with that, Deepak will tell us about LinkedIn.
So thanks all for inviting me. So I'm going to talk about how we are using machine learning and optimization to do advertising at LinkedIn. And so before I begin, this is more a applied talk. I'm not going to talk about new methods. I'm going to talk about how you can take all the awesome academic methods that are out there and apply it to an industrial application with success, right? So here is an example of how we do of where ads get shown at LinkedIn. So if you go to the LinkedIn front page, this is an example of a display ads that is shown to users based on their professional identity and other targeting attributes. Here is another example where we show ads within the stream, the network update stream as we call it in LinkedIn. So there are many other places. If you go to profile pages, you see ads. If you go to search pages, you see ads. Ads are ubiquitous as in any other web-centric company, right? So here is a rough flow of how the advertising system works. Again, I've oversimplified the process, but still it gives you a high-level idea. So we get an ad request when a user is visiting some page. And again, with the ad request comes all the information about the user, like what region they are from, what is the age of the user, where is this request coming from, what is the size of the real estate where the ad has to be placed, and so on and so forth. This goes to the ad server, and the ad server filters out a bunch of campaigns based on some targeting criteria that are usually specified by the advertiser. So the advertiser might say, don't show my ads except for Facebook engineers in Silicon Valley, right? If you are Google, you might do that, right? I just want to target Facebook engineers, right? And then, we are not going to show you any other ads except for Facebook engineers, right? If an ad has been seen by a member multiple times, we don't want to prolong their agony any further, so we stop showing that. We also do things like budget pacing. I'm not going to go into that, but that's again a more technical thing. Once that is all done, then we send the ads to a module which selects the format in which the ad should be displayed. So this is more the look and feel of the ad, right? Should I write the text in bold? Should the color of the ad be blue or red, and so on and so forth, right? And it does make a difference how you present these ads to users, right? And then finally, it goes to a response prediction engine, and the response prediction engine predicts click-through rates when an ad is going to be shown to a particular member. And once that is done, we sort the ads by bit times CTR, or expected revenue. And that's how the ad gets displayed. And if a user clicks on the ad, which is not very often, but they do click on the ads sometimes, that's how our bills get paid, then we kind of run an auction, and it's a second price auction. The winner pays the minimum price required to win the auction, right? So that's the whole flow. So I'm going to talk about the response prediction parts in this talk, right? And so there are 2 different places where we use response prediction. One is to select the right format to show the ad to the user, the look and feel. So we have web devs that create a bunch of formats, like a few 10s or 20 of those, in different look and feel. And the goal of machine learning here is to figure out what is the best format to show to each user, right? That's one problem. Once we have selected the format, then the goal is again to use response prediction to pick up the top ads to be ranked by expected revenue. So let's start with the warm-up exercise of how we select the right ad formats automatically through machine learning, right? So we have a bunch of page types. So it could be home page, it could be profile page, it could be search page, and so on and so forth. So a bunch of page type, and for each page type, you have a bunch of admissible formats that have been created by the web devs, right? And again, a simple approach would be, you count clicks, you count views for every format for every single page type, and then you rank the formats by the click-through rate, right? Clicks over. This is a very simplistic approach, okay? So this doesn't work. Why? What happens if there is a new format that gets introduced into the system? How do you onboard a new format? How do you avoid starvation of an old format that have been prematurely terminated, right? Maybe the user did not click on the ad for the first 4 times it was shown, and so the click-through rate is 0. That doesn't mean that the format is bad. It was just, it had an unlucky streak to begin with, right? So how do you mitigate these issues? So this is also known as the explore-exploit dilemma in the machine learning and statistics literature. If you are familiar with that, of course, you know what I'm talking about, but if you're not familiar with that, I'm just going to do some small animation and show you, right? So imagine there are 4 different formats that are in the system, and again, those are the statistics that we have accumulated for these formats. You'll notice the last one is the one that just got into the system, and we have some historical data to guess that the CTR of that is something like that, right? And, oh, sorry, I think the previous slide had a different typo. You know, the click-through rate should be 2.5 and so on and so forth, so I apologize for that. Right? So suppose you have this scenario. Now, how do you decide what fraction of traffic to allocate to each of these formats? Right? So if you take a greedy approach, you would, of course, decide that 100% of the traffic should be allocated to format 3, and the others should be terminated immediately. Right? But again, as you see, that's not the right approach, because the other formats do not have enough data for us to be making such a decision so early on. Right? So you might say, okay, well, why don't we randomly allocate equal amounts to all format? Now that is, yes, that is democratic, but democracies don't work very well, especially when you're doing algorithms. So that's highly suboptimal. So that's not going to work. And so something in between is what works, right? So for instance, you know, if you do something like a soft max instead of a max, right? So allocate traffic proportional to your current CTR estimate, maybe perhaps tempered by some temperature and so on and so forth. That may give you a better allocation, right? It helps you exploit formats that are known to be good, but it also helps you explore formats that are potentially good, right? And that is how you maximize your overall performance of the system, right? So there are many explore-exploit schemes in the literature. I'm not going to go through that. So what we do is we evaluate several explore-exploit schemes by doing offline replay analysis, and again, this is something that was done by John. So we use that heavily. We test a series of explore-exploit schemes, and then we launch the ones that look promising in offline analysis. And you know, for this application, you know, most of the usual explore-exploit schemes seem to be working quite well for us. It does make a difference as to how quickly you update your CTRs if you have many new formats coming in the system regularly. In our case, we don't get many new formats coming to our system very quickly, so for us, updating the CTRs on a daily basis is okay. But anyway, so this was just a warm-up exercise, and you know that the format selection problem was an easy one. You have a small number of formats. We tried running algorithms to personalize format based on gender, geo. That doesn't matter. What really matters is the size of the real estate and where you're showing the ad. That is the most important characteristics in this problem. Others did not matter too much. Right? So in some sense, it's an easy problem. Okay, so now let's come to how we will estimate the CTR of ads. Once you have selected the right format, you have to fill up those slots with the best ads. So you still have to compute the click-through rates when an ad is shown to a user. And here, member or user attributes do matter quite a bit. You have to personalize the estimates of the CTR, otherwise you don't do a good job, right? So it is important to estimate CTR for this particular application at more granular resolutions than what we were doing for the format selection problem, right? So you have to create more segments, maybe based on user's industry, based on user's age, education, what they have done in the past, which company they worked for, which company they moved to, and so on and so forth. A lot of information. Plus, we have all the behavioral data as well, right? What they have been doing on the front page, what they have been reading, whose profiles they have been poking, who has been poking at their profile, and so on and so forth, right? So a lot of information, right? So how do you use all that information which we have about users, both the identity and the behavioral data, and kind of do a good job of personalizing these CTR estimates, right? So that's what we want to do. And again, you know, this is the usual machine learning problem. So if you choose too few segments, then you fail to personalize. So you have more bias in your estimates, of course. If you choose too many, then you end up in data sparsity and you have high variance. Like, for instance, if you chop your data into very small pieces, then most of the segments will have 0 clicks, right? And again, it's just it's a matter now of distinguishing 0 over 5 from 0 over 50 from 0 over 5 million, right? That's really the crux of the problem. So in order to solve that problem, we have to pool data by segments to mitigate data sparsity, right? And here is an example, right? So if you want to estimate the CTR of an ad ID 77 on a profile page for a user from Palo Alto, you may not have enough data, right? This ad may have been shown only 5 times and you observe no clicks. So that's not going to help you get reliable CTR estimates. So what you may want to do is you might want to piggyback on the overall CTR for visits on the profile page, or you might piggyback on the overall CTR for users from Palo Alto. These are some examples of features, if you will, which you can construct to kind of come up with a good estimate or reliable estimate for CTR on that particular cell, right? And again, there are many different ways of doing this pooling business in an effective way in machine learning. You can use many techniques, decision trees, random forests, gradient boosted decision tree, but we decided to use logistic regression, right? And again, there is no particular reason why you should use or you should not use logistic regression. It was just a matter of convenience, and logistic regression for these class of problems have been shown to work very well in practice, right? So that's the only reason. But the principles I'm going to describe later on in the talk could be applied to other models as well. There is no reason why you can't apply the same principle which I'm talking about, even if you're doing a decision tree, for instance, right? Okay, so again, for those of you who don't know what a logistic regression is, this is not for machine learning, trained machine learners. So suppose you're trying to fit a logistic regression in 2 dimensions, and again, both these dimensions are continuous, Gaussian, all that stuff. You have some historical data in these 2 dimensions. Some of them are positive, some of them are negative. So what logistic regression does is it finds the best line that separates the positives from the negative, right? And then if you have a new point and you want to predict the probability of a click, you look at the distance of this point from that best fitting line and read the probability from that sigmoid function, right? So that's essentially at a high level, that's what logistic regression is. Now, you can kind of look at what the logistic regression would look like mathematically, right? So you have features available for users, again, based on all their identity and behavioral data. We have features that we extract from the ad itself, like all the keywords, all the text you write when you are actually submitting the ads to our system. We also have information about the context in which the ad has been shown, like what kind of page is the ad being shown on, what position is the ad being shown on, what device is the ad being shown on, is it mobile or is it desktop, and so on and so forth, right? All right, so I here denotes the user ID, J here denotes the ad ID, and K here denotes the context ID, right? And we have historical data that gives you responses when ad J have been shown to user I on context K, right? We have tons and tons of data, right? So what logistic regression does is it assumes that this is a Bernoulli model, right? It's a coin toss experiment with probability Pijk, and then on the log odds scale, it assumed that this probability could be, the log odds could be expressed as a linear function of all these features which I talked about, right? So this is what we call the cold start component, right? So these are, this component is only a function of features which you can extract for users, ad, and context, right? And this is something which can be trained on tons and tons of historical data. It does not change very rapidly. We kind of train this component once a week. And then the second component is what we call the warm start component, also called the random effects in statistics, if you're familiar with that, right? So this component is not good enough to capture all idiosyncrasies of an ad, right? So if you can do a very good job of feature engineering and extract everything about the ad, then this component would not be needed. But unfortunately, that is very hard to do. So despite of however well you do in this particular component, you still would have some residual idiosyncrasies that are not explained by this particular component. And that is what this component is capturing, right? So J here is the ad ID. So you are building a per ad adjustment on top of this cold start component, which is explaining the probabilities using just the feature vectors for ads, users, and context. So this is the cold start component, the stable component. This is the warm start component, which is capturing more the residual idiosyncrasies, okay? Okay, right? And so model training, right? So the cold start, again, as I said, is trained on large amounts of historical data, billions of observations, thousands of features. The training is done on a regular vanilla MapReduce framework. We did not create any new infrastructure for doing that, and I'm going to explain how we do that. The warm start, once we have trained the cold start, the warm start component is used as an offset, and then we fit an independent logistic regression for every single add ID. Right? So once you freeze the cold start component, you can actually create an independent logistic regression for every add and just kind of run them in parallel. Right? So again, a very easy thing to do on MapReduce. Right? So the computations here are rather trivial because of the way we do it. Right? So the second component is rather easy. You can easily parallelize on MapReduce. Now I'm going to talk about how we parallelize the first component on MapReduce. Right? That's not so obvious. Okay. So in order to do that, we use, so I've already gone through this. I'm not going to go through the MapReduce slide. You spent 1 hour explaining MapReduce. So done, all right? So this is how one could think about doing it, right? So a naive approach would be you partition your data into multiple components at random. You fit a separate logistic regression to each component, and you average the result, right? That's a naive approach. Now that's okay, but it is not guaranteed to converge to the global solution which you will get if you had run the algorithm on the entire data set, right? So fortunately, there is an algorithm which has been popularized by Stephen Boyd at Stanford called the ADMM algorithm, right? So what the algorithm does is it does a scatter and gather approach of computing things, but it sets up constraints, and the constraints are every partition's estimate has to be constrained to be equal to the global estimate. Right? So when you're doing this computation, you have a bunch of small logistic regressions. You get independent estimates from these logistic regression, but we kind of add a constraint on top of that which says that every single logistic regression should be equal to the global consensus estimate. Right? So you can cast it as an optimization problem, and if you can solve this optimization problem, which actually could be done in a scatter and gather approach, I'm going to show you in a minute, you are guaranteed to converge to the global optimum if you kind of do a lot of iterations. Okay? So this is how it works. If you draw a picture, right? So you have big data, you partition things, you do independent logistic regression in each of these boxes, then you do some consensus computation which is driven by the constraints, and then you kind of pass back information which you got from the first iteration to the partitions, again redo computation, and then you keep doing it until you converge, right? So again, you can write down the optimization as follows, right? So this is the logistic regression per partition subject to this constraint, right? Beta equals to beta, right? This is exactly what ADMM does, and for the L2 regression, this is what the equations look like. So essentially in every box you are doing local regression shrunk towards the best global estimate you have so far, and then once you get the local estimates, you kind of do a consensus estimate and again pass it back for the next iteration, right? So it's a scatter and gather approach, no communication between the processors at all. Okay. Okay, and so we made some changes to the ADMM algorithm. So first of all, initialization is very important for ADMM. If you initialize your estimate by just doing this naive scatter and gather approach and doing the consensus estimate, that improves the convergence a lot. Secondly, the step size which you have in ADMM, that has to be selected carefully. So if you make it adaptive, that also helps convergence quite a bit. In fact, in our experiment, we saw that these two simple optimization reduced training time from 10 hours to 2 hours, and here is a curve which kind of shows this. Okay? So this is how we do this. Now the next thing is how do you do explore exploit in this particular scenario when you have logistic regressions. Again, the idea is very simple. So this is the cold start line. And then for every add, we have a warm start, right? And we don't add any statistical uncertainty in the cold start part because we assume that that component has been trained on tons of data. There is not much statistical variability going on here. Most of the statistical variation is going on in the warm start part where we run a per add model, right? So if this is the model, so what you do is for every warm start component, you have a posterior distribution. And when you're serving the add, you draw a random number from that, which is essentially drawing a random line for the second component and add that and kind of start serving the add, right? So that's how you do the cold start component. It's also called Thompson sampling in the literature, right? So I'm going to show you, so for the sake of showing results, I'm going to kind of have, I'm going to use some names here. So laser, this is going to be the logistic regression which we ran without the Thompson sampling scheme. I just described. So it is, Thompson sampling is nothing but just adding some jitter to your estimate. That's all it is, right? And the jittering is done based on the posterior distribution for every add, right? And then laser E is the logistic regression, which we do by using this jittering or explore exploit, as I described, right? So let me show you some results. So these are some results from offline analysis. So control here is the model that LinkedIn was running last year. I can't describe what that model is. I can describe it offline maybe, but I don't have time to describe what that was. Code only is, so this is a model which was run without using any ad-specific adjustment, just the feature-based adjustment. And this is the model which we used both the feature-based adjustment as well as the ad-based adjustment. And you can see that if you look at the AUC and ROC curves, of course, these two are better than the others. These are some results which we obtained from online experiment, right? So whenever you're running these tests, you always tend to over-predict because you're selecting the best out of a bunch of things. And so, by definition, there is selection bias, and you tend to over-predict your performance, right? So one good measure of accuracy is how much your model is over-predicting for different ads or different campaigns, right? So 1 here are campaigns where we have very little data. 8 here are campaigns where we have collected a lot of data. And as you can see, the over-prediction increases as you go from the campaigns with scarce data to campaigns with a lot of data, which is expected. But the amount of over-prediction is much less with the new class of model which I described compared to the control model that LinkedIn was running, right? So this is, again, all results which we are obtaining from online tests that are running in the system. I can't reveal the lift numbers which we got in production, but again, here is an example which shows you the eCPM lift or the revenue lift per impression which we get by running these models in production systems, right? So this is 0%, and you can interpret it in any way you like, but at least what this is showing you is there is a consistent improvement in performance every day when we run this test, right? So this test was done for 6 months, and now the whole system is kind of running based on this system. The old system is all deprecated. Now this is the new system which is running at LinkedIn today. Okay?
Why is there a beep of 4?
Pardon?
Why is there such a big beep of 4, a big 4 here?
Okay, that's a weekend.
Okay.
Where we get traffic from France and other places. So we're not doing very well in France, so that's good. Okay, so here is another plot which I want to show. Sorry. I think there is one line that is not okay. There is one line with a different color which is not appearing due to the font. Okay, so I wanted to show this plot to show the difference between the explore exploit bucket and the exploit only bucket. So what happens is if you look at the exploit only bucket where there is no jittering going on, then you see a consistent lift for all types of campaigns which have little data and campaigns which have very high data. But if you look at the other bucket, which is this one, you see a huge loss in revenue for these buckets. But as you go up, you see a big improvement in these buckets. And that is expected because when you're doing jittering for ads that are very new, you don't have enough data, you don't have good estimates, you're going to overestimate the CT and you're going to select the wrong ads more often. But that helps you generate learning data which is used by this particular model to do a good job, right? So again, I think this was a subtle point. I can't explain it without the picture. It is very difficult, but there are some subtleties going on when you do explore exploit versus when you don't do explore exploit. Okay. So to summarize, the main point was the main point I want to make here is reducing the dimension through logistic regression and coupling it with an explore exploit scheme like Thompson sampling looks like an effective mechanism to solve response prediction problem in computational advertising. If you partition the model component as cold start, which is based purely on features, and warm start, which is capturing residual idiosyncrasies at the ad level and campaign level, then that's an effective mechanism to scale your computation. You can do the first computation at very coarse granularity, and you can do the second computation very fast within few hours. So that's a very good way of scaling computations. And if you use ADMM with a few modifications, it is an effective model training strategy for large data with high dimensionality. And again, these methods have been working pretty well for us in LinkedIn advertising. It has provided significant improvements so far. These are my collaborators. By the way, this picture is not what he looks like, but he prefers to use that picture. So current work, we are investigating Spark and various other fitting algorithms to scale up the ADMM algorithm even further, and we have obtained some promising results. ADMM still looks good on our data sets. We are spending a lot of time working on how to do stream advertising, right? So stream advertising is not all about predicting click-through rates. You have to predict click-through rates, you have to predict share rates, you have to predict likes, you have to predict comments, and you have to combine these estimates to come up with a good measure of what user engagement means. So highly, very challenging problem. Filtering low-quality ads is very important on the stream because if you're seeing your friend's update and then suddenly you see a bad ad, you'll stop seeing your friend updates as well and stop coming to LinkedIn. So we have to be very careful when you're injecting ads within organic content, right? And that's why it's a hard problem. So that's something which you're working on. We are also working on stream recommendations. How do you recommend updates on your stream, right? If you have different kinds of updates, job anniversary from your friends, something that has been published by the company you follow, something that have been published by the influencers you follow, something that your friends shared on the network. How do you take all that content and the advertising which we want to inject and do a holistic job of providing a good stream to the user? That's, again, a very challenging problem, and you're working on that right now. Finally, we are investing a lot in building large-scale machine learning infrastructure at LinkedIn, similar to the methods I just described. That is powering a lot of other recommendation problems we have on LinkedIn, like gym, for instance, jobs you may like, people you may like, and so on and so forth. Groups you may like, a lot of other recommendation problems as well, right? And so finally, we are hiring. We have slots for shameless plug, but yes, this is a good opportunity. If you're interested in this kind of work, taking cutting-edge machine learning work and putting this into production and making a difference to real-life application, we are hiring. Let me know if you are interested. And that's it. Thank you.